Today we're going to be talking about Thevenin and Norton equivalent circuits. These are based on Thevenin and Norton's theorem respectively, and they're effectively an alternative way to make any two-terminal network look like a practical voltage source in the case of Thevenin's theorem, or look like a practical current source in the case of Norton's theorem, where we know that practical voltage sources and practical current sources can vastly expedite our power analysis of DC circuits from our last lecture. So let's look at Thevenin's theorem. Thevenin's theorem says any two-terminal linear network may be replaced at the terminals by an electrically equivalent voltage source, VTH, in series with a resistance RTH, where VTH is defined as the open circuit voltage seen across the terminals of the live network, and RTH is defined as the resistance seen looking in through the terminals of the dead network. And I find that it's best to actually learn this technique using circuits as examples. So the circuit that we're going to analyze first is this guy, where we'll have a 5 amp source connected to a 2 ohm resistor, connected to a 8 ohm resistor, a 10 ohm resistor, and then what we are going to do is we are going to find the Thevenin equivalent circuit as seen by this load resistor RL. So what this means is I'm going to split this circuit up into two parts. So on the left-hand side of my purple dashed line, I'm going to call this network A. And on the right-hand side of my dashed line will be network B. Okay? So we are going to try to determine the Thevenin equivalent circuit for network A as seen by network B. Okay? So anywhere that we can draw a pair of terminals, we can effectively disconnect network A from network B and vice versa, and that will allow us to compute the Thevenin equivalent circuit. So we are told that the Thevenin equivalent circuit has two portions, a voltage source VTH in series with a resistance RTH. So let's start with the voltage source, where VTH is defined as the open circuit voltage seen across the terminals of the live network. So the open circuit voltage means, I'm going to redraw our circuit real quick. Gosh, that's getting crooked. There we go. That's probably just as crooked. 2 ohms, 8 ohms, and here is our 10 ohm resistor. Okay. So I've redrawn network A entirely, disconnected it from network B. Our open circuit voltage is the voltage seen between this pair of open circuit terminals. That's all that means. So the open circuit voltage, or the Thevenin voltage in this case, is just the voltage drop over the 10 ohm resistor. How could we determine the voltage drop over the 10 ohm resistor? Well, the short answer is any way we feel like. I'm going to use nodal analysis because I can see that this is going to give me a simple 2-equation, 2-unknown system, or I'll be able to solve for VTH directly. But you could just as easily do mesh analysis, where you would find the current through the 10 ohm resistor and then multiply that by 10 ohms to get VTH. I think you could do this using a source transformation here. Actually, that's probably the easiest way. A source transformation for this 5 amp source and this 2 ohm resistor would put a 2 ohm resistor in series with an 8 ohm resistor, in series with a 10 ohm resistor, in series with a voltage source, and then we could simply do voltage division. So I've changed my mind. That seems like the easiest method, so that's what I'm going to do. So using the source transformation technique that we learned in the last lecture, 5 amps in parallel with 2 ohms is going to be 10 volts. Since the arrow is pointing up, I'm going to put the positive polarity terminal on top, negative polarity terminal on bottom. My 2 ohm resistance should be in series. And now, using voltage division, VTH is going to be 10 volts multiplied by 10 ohms over 2 ohms plus 8 ohms plus 10 ohms is equal to 5 volts. So it is literally that simple to determine the Thevenin voltage, at least for this particular circuit. But that process is what you would do in any circuit. All you want is to find the open circuit voltage between the 2 terminals that are left behind by disconnecting network A from network B. How you determine that voltage is irrelevant. You just need to be able to do it. So you can use any circuit analysis technique that you're comfortable with. So again, I suggested using nodal analysis. Many of you are probably more comfortable with mesh analysis, so you could do that. We saw that you could do it using a source transformation and then applying voltage division. I'm sure there are other ways as well. So now let's talk about the Thevenin resistance. So for the Thevenin resistance, we are told it is the resistance seen looking in through the terminals of the dead network. The dead network means that we have to turn off all of our independent sources. So we're going to have our network disconnected at our terminals like we had before, where this is our 10 ohm resistor. Here's our 8 ohm resistor. Here's our 2 ohm resistor. And then our current source, if you recall, turning off a current source means replacing it with a pair of open circuit terminals. So now we have 2 pairs of open circuit terminals. That might be confusing. But remember, we're looking in through the terminals that were created when we disconnected network B. So we know that we're looking in this direction and trying to find RTH. So these open circuit terminals that are the current source turned off really aren't contributing anything, so I can just as easily erase them. I see then that I have a 10 ohm resistor in parallel with 8 ohms in series with 2 ohms. So that's 10 in parallel with 10. RTH is simply 5 ohms. And from that, the electrical equivalent Thevenin circuit for our original network is this. So we have replaced this current source that's connected in parallel to this resistor network with a practical voltage source containing a 5-volt source and a 5 ohm resistor. That is how you determine a Thevenin equivalent circuit. Now we're going to talk about how to determine the Norton equivalent circuit for an electrical network. Norton's theorem states that any two-terminal linear network may be replaced at the terminals by an electrically equivalent current source, INO, in parallel with a resistance, RNO. Excuse me. So it just says that we can replace any two-terminal network with a practical current source, where INO is defined as the short circuit current seen through the terminals of the live network, and RNO is defined as the resistance seen looking in through the terminals of the dead network. So one thing that I want to point out is that the definition for RNO and RTH, the Thevenin resistance, are the exact same thing. So if we've already found the Thevenin resistance for a circuit like the one here, we can just use the Thevenin resistance as the Norton resistance and not lose any information whatsoever. So what we're really going to focus on right now is then how to find the Norton current. All right. So the Norton current is defined as the short circuit current. So we again have the same network A and network B, and we are going to disconnect network A from network B. So here's our 5 amp source, our 2 ohm resistor, our 8 ohm resistor, our 10 ohm resistor. Here are our terminals where network B used to be connected, and we're told that we want the short circuit current. So that means we are going to place a short circuit across the terminals of our network and calculate the current that flows through that short circuit, which will be this guy, INO. Now, again, we could do this or determine the current INO in any way that we are comfortable with. So we could do nodal analysis, mesh analysis, Kirchhoff's voltage law, Kirchhoff's current law, whatever we want to do. Again, this is a place where doing a source transformation will make determining that quantity very, very simple. So our 5 amp source with our 2 ohm resistor becomes 10 volts, positive polarity on top, negative polarity on bottom. Our 2 ohm resistor is put in series with that voltage source. Now notice this short circuit is in parallel with this 10 ohm resistor. So the current that's leaving this 10 volt source is going to flow through this 2 ohm resistor, flow through this 8 ohm resistor, and then come to this node. And it's going to see a path with 10 ohms of resistance and a path with 0 ohms of resistance. So all of the current that's leaving this 10 volt source is going to flow and be our Norton current. So from this, our Norton current, I Norton, is 10 volts divided by 2 ohms plus 8 ohms is equal to 1 ampere. The methodology that I've used is, and by that I mean placing a short over our open circuit terminals that we got disconnecting network A from network B, is how you determine the Norton current. Your analysis method to get a number for I Norton is irrelevant. You can do it however you are most comfortable or whatever seems like the most efficient way for you to do it. You should get the same answer regardless of the circuit analysis method that you choose. So, the Norton equivalent circuit then is a 1 amp source in parallel with a 5 ohm resistor that is in parallel with our load resistance RL. So these two are electrically equivalent. And it shouldn't be hard to tell that the Thevenin equivalent circuit is simply the source transformation of the Norton equivalent circuit and vice versa, giving us the relationship V Thevenin is equal to I Norton times R Thevenin, or I Norton is equal to V Thevenin divided by R Thevenin, or something that we're going to actually use when we get into Thevenin and Norton equivalents with dependent sources. R Thevenin is the Thevenin voltage VTH divided by the Norton current.